Thanks everyone for coming. One note before I begin. In the abstract for this talk, I said that I would give a live demo. Due to some glitches, I'm not able to do that. So this will just be a talk only. That said, the agenda for today is I'm going to talk about motivation. I'm going to give you a high-level overview of the data pipeline I'm using. I'm going to talk about hardware for a bit, and then I'm going to do a little deep dive into the pre-processing that I'm using for this system. So I'm Keita Broadwater, as he said. I've been in tech for about 15 years. I'm currently the co-founder of Oxygen AI. Oxygen AI is a consulting company that specializes in helping small to medium businesses and organizations leverage data science and AI to drive good business results. I'm also the co-founder of PV Tech. That's a solar energy company that I sit on the board of that has operations in East Africa and Southern California. So what are we talking about at a high level? The system that I'm developing is one that uses sensors, specifically accelerometers, to do an interrogation of footsteps. These accelerometers are placed on the floor of a room or in a building, and taking the signals from these footsteps, we're able to use analyses and machine learning to draw out information like what is the identity of a person in a room, how many people are in a room, and other information. So why is this worth pursuing? A lot of times when I talk about this to people, they ask me, well, why not use a video camera? Well, I think that this technology fits a niche that balances what I would call intrusion versus intelligence. So think about the types of technologies that can give you some information about what's going on inside of an area. On one end would be something like an IR sensor, used for motion detection, but not much else. On the other end would be a video camera. If you combine that with recognition technology, you can get lots of information about what's going on in a room. But in some cases, particularly when you have concerns about privacy, a lot of information could be too much information. So for example, a video camera can tell you that, with recognition technology, it could probably tell you that I walked into a room if it could recognize my face. It can also tell you that I'm picking my nose. So in cases where you want to have privacy for people, having a system that can draw out good information but not put people in compromising positions, so to speak, is compelling. So an overview of my pipeline is, so I'm using sensors based on, right now I'm prototyping this, so I'm using sensors based on Adafruit and Arduino. Those sensors stream data into Kafka that goes into Spark streaming, specifically structure streaming data frame. I use a series of transformations to transform a signal from an accelerometer into an image that I can use in the machine learning model. So a bit about the hardware that I'm using. I'm using an accelerometer that's on an Adafruit chipboard. And I'm also using a wireless microcontroller. So for this microcontroller, you have two chips. One is a controller chip that you can use to control the sensor. The other is a Wi-Fi chip with a Linux operating system on it. And this is what I use to create, when data is coming through from the sensor, I use the Linux operating system chip to create a TCP socket and then stream that to a server, which places the data onto a Kafka producer. The next step I want to go with this, and it's easy to do with this type of board, is since one of the chips on this microcontroller board has a Linux operating system, I can create a Kafka client directly on the board. So the next step for me for this part of the pipeline is to completely overstep the mid server that I'm using and place a Kafka client producer on this board directly. So pre-processing consists of a few steps. One is taking a raw data signal from the sensor that I just described, breaking it into overlapping frames, and on those frames performing a wavelet transformation, which I'll go into detail in the next slide. This transforms a problem from a time series problem to an image problem. So once we have the image, we flatten it, and we do dimension reduction on that image. And then we can use it to train or to get predictions from a machine learning model. So what are wavelets? Wavelets are short-lived waves that have a mean of 0. They're perfect for this application because when you have footsteps or when you have activity in a room, it's really very localized and it's non-stationary. You can see an example here. One piece of data shows a person walking into a room, getting very close to the sensor, and then going away from the sensor. So it's much better to use transforms to interrogate these types of signals than to use a Fourier transform. So when we do a wavelet transform, we take a wavelet function and we decompose a signal into two spaces. One is space, one is translation. And a lot of times people use these as analogs for frequency or yes?
When you said it's better than a Fourier transform, do you mean that because it's reading out a better answer or because it's more efficient? Because there's kinds of wavelets that could make both arguments, but which one are you talking about?
I think that, so, wait, could you repeat the question? I'm sorry.
So you said you compared the wavelet that you're using to Fourier transform.
Right.
And you said it was better, but did you mean better because it can be more efficiently computed or better because it reads out a better answer?
Because it reads out a better answer. It reads out a better answer because the signals that we're interrogating are very localized and they're non-stationary. So.
Oh, I see. I guess I was picturing a windowed BTFT, which would give you the localization. But
So there are some ways that you can use Fourier transforms. There are some ways you can use window Fourier transforms for sure. Yeah. Okay. I think it gives a better answer. Thanks.
You get the localization capture.
Yeah. Thanks for the question. Yeah. So once I perform a Fourier transform, I create an image by creating something called a scaleogram. So we're dealing with scales, not frequency. And if we were doing something else, we would call this, if we had frequencies, we would have a spectrogram, but right now we're dealing with a scaleogram. So this scaleogram, or something like it, becomes the image that I use to train a model and to interrogate a model. So there are several packages that exist for this to create wavelets and to do wavelet transformation. I use Pi wavelets. I think it's a very comprehensive one. It has lots of types of wavelets, both discrete and continuous. There are also lots of packages that deal with seismic data. OBSPi is one of those packages that has a pretty good wavelet functionality. There are also wavelet packages and modules in Java and Scala. So what I like to do in the end is have everything in Scala. At this point, though, I'm using Pi wavelets to patch on some custom functions using Pi wavelets and some other modules. But I want to use the Scave module eventually to have everything within Scala for the transformations. And so the code there you see is just an example of using a wavelet packet transform, using a specific one called a Doboshay 20 tap wavelet on a piece of data. So I can use this code to create a wavelet, which will be a matrix of coefficients. And then I can use those coefficients to create the scalegram image that you saw. So the second part of pre-processing for me is to take a scalegram. In this case, the image that you see is a scalegram for a discrete wavelet transform. Take that. In a lot of cases, you have an image with hundreds to thousands of features. So you want to create, you want to do some dimensionality reduction. How I accomplish this is just to brute force, take quite a few methodologies, so I'm using scikit-learn for this. I'm using quite a few methodologies to to find the right parameters, find the right function that will give me the best F1 score, the best precision and recall scores in my machine learning model.
Quick question. What do you consider a feature here? Each one of the wavelet like scales and
so this is a scalegram. So this is considered an image with pixels. I flattened it, so each pixel becomes a feature in this case.
And you don't do any pre-processing on that image, so to say, like any convolutions or something?
No. I found that I thought it may be necessary, but I found that some of the results that I'm getting, as far as from the classification models that I'm using, have been pretty good without going that far.
How big is it eventually? Like
You mean an image like this?
the feature? How many features?
So for this example, this is 1,120 features. So for this example, I take the 1,120 features and reduce it down to 8 features using a non-negative matrix decomposition. And how I got to that method, non-negative matrix factorization, and 8 features, is by, as I said before, just kind of doing a brute force, kind of a grid search type of way, testing several types of decomposition methods, and a range of feature numbers. So I think I went from 5 to 100 to see what would give me the best results in the trained model. So at this point, I was going to go into the live demo, but as I said, I don't have that demo available now due to some glitches. So I'm just going to close out and say that using wavelets I found is a very good way to get results that have high precision, high F1 scores when you do classification on gates and footsteps. And that I found that it's very possible now to have an end-to-end, very low-cost system that can do very accurate characterization of activity within an area, within a building. And so the next steps for me are to have everything in Scala, have it end-to-end, and increase the scale of the number of sensors that I'm using, and increase the sampling rate of the sensors that I'm using. So right now, I'm driving the sensors at about 100 samples, 1,000 hertz, and I want to ramp that up to a greater number in the thousands of hertz. That's all I have for you. Thank you very much. Yeah. Oh, yeah.
We've got time for a few questions. So, thank you for great talk. I have a question. Can these sensors be used in outdoor environment?
Can they be used in an outdoor environment? They can, but it just depends on the packaging. The ones I'm using now, I'm using indoors, so I don't use any kind of hermetic packaging for the sensors. But you can create yourself, especially now with a lot of the 3D printing technology. You can create a hermetically sealed package that you could deploy outside.
And how about sensitivity?
Sorry again?
How about sensitivity? Because inside the room you can have like high vibrations, but outdoor if you put on the real ground, it can be like different environment.
Oh, I see. Yeah, so I think it also depends on the packaging, and it depends on the type of sensor. So most of my work has been inside, indoors. So I can get away with using a very low cost sensor like you see here, and getting good results still. Outside, usually when people are doing seismic analysis, they use seismic sensors. They're a little, the design is a little more hefty, and the range of the sensors are much greater. And using some techniques, you can isolate footsteps, you can isolate cars driving by, and things of that nature. So you need a different type of sensor, and you need more robust packaging to do that, but it can be done.
Can you give us any comments on, physically what's happening with the sensor? Is it just taped to the floor, or, I mean, is there anything that you found that's like, do this, don't do this, kind of, if you do this, noise problems. And second question would be, which of this processing do you eventually hope to run at the edge on the node before you push it to your cloud?
No problem. So what it's doing, so I'm using basically an adhesive just to put on the floor, not a non-permanent adhesive. So it's not really doing anything, it's sitting there and it's getting the vibrations from whatever activity is going on. So it could be a human walking, it could be a Roomba traversing the floor, it could be a pet. What got me into this project was a year ago, I was woken up in the middle of the night by something bumping furniture downstairs. So I went downstairs. I thought I was going to have my moment of truth, protect my family and homestead. But it turned out to be a Roomba that was misprogrammed. Instead of 4 p.m., it went on at 4 a.m. in the morning. So then I was thinking, okay, it would be great to have an app on my phone that could just tell me, don't have to worry, this is a Roomba, just turn it off. So it's it's just sitting there. It's just a passive sensor for the most part. And your other question was,
how much do you want to run on the sensor node before you ship the data eventually? I mean, I know right now it's a prototype, but
I mean, I would love to be able to. I don't think that Yun controller can accommodate this, but I'd love to just be able to do the transformation directly on the board. But I think what's more realistic is that I'd at least be able to put the Kafka client on the board instead of having a third, an unneeded computer running that server. So yeah.
we've got time for one more question.
I guess my question is more theoretical, which is, do you have any sense of what the limits of sort of uniqueness of gate is? They say a fingerprint, I don't know, it's 1 out of every billion or something. I don't know. It's not completely unique. So I'm curious, have you done research on how unique someone's gate is?
Thank you. I think there has to be limits. I haven't reached them yet. One of the good things about this type of system, this type of project, is that if I need data, I just put a sensor down and walk past it, or put a sensor in a crowded building and have people walk past it, or finagle my wife into walking for a few minutes to give me more data. So, but I haven't done those studies. To do that, I think is going to require some large-scale labeling efforts. So while I can go and lay a sensor down in a crowded hallway and do some unsupervised clustering to figure out if there's some limit to the uniqueness, I think probably to get the answer, I'd need a statistically significant number of people to determine that. And I haven't done that work.
So let's take a moment to thank Keita and
Thank you.